Welcome to Linear Perspective with Marshall Vandruff and Leonardo da Vinci. Perspective gets complex, but we will solve the complexity one simple point at a time, beginning with what the word perspective means. It comes from the Latin word which means to look through. It's all about creating on a flat surface, like a piece of paper, the illusion of a deep world. If we put lines on a piece of paper, they could be just lines on a piece of paper, but they could also be a window into a world. And if we get closer, or closer still, the illusion is created basically by lines on a surface. If we take some diagonal lines going one way and some diagonal lines going the other way, and put them together so that they make some diagonal lines going both ways, they could just be diagonal lines, but they could also be a view of a musical instrument. And if we move closer to it, it may seem like that corner comes even closer to us, but if you put your fingers on the screen, don't put your fingers on the screen, just pretend. This corner is no closer to us than the far one. It only seems that way because of these lines. This is a game we play. We take a flat surface with some angles on it, and it looks like deep space. That's what perspective is. Before we get to how it works, let's define some terms. We're going to begin by studying the private language that artists use to communicate with each other and to impress outsiders. Let's begin with angles, or how straight lines relate. Here's the first term, right angle. You may know that a right angle is 90 degrees because a circle, if it's divided into 360 equal parts, 1/4 of that makes this angle, and so we call it a right angle. Or we can say that these red lines are perpendicular to each other. And it doesn't make any difference whether the L is facing to the left or to the right, or whether we throw another red line in there that will be at right angles to the one below it, or if we put another one across there. Every line on there is either at a right angle to the others or parallel, but we'll get to parallel. Right angle, squared up, L-shaped, like that. Now, parallel is easy to remember because if you spell it correctly, the two L's are parallel to each other. And it doesn't make any difference whether these lines are vertical or horizontal or diagonal. If they are going in the same direction, they are parallel. Well, what's left over? Any line that is not at a right angle to the other line or parallel to the other line has got to be oblique. That's all that's left over. The other lines are oblique, but there are two kinds of oblique. Some oblique lines are obtuse. That means more than at 90 degrees to each other, making a blunt arrowhead. And then there is acute. So we have obtuse, and we have over here a sharp, flesh-lacerating arrowhead known as an acute, and it makes no difference whether it's facing to the left or facing to the right. It is the sharpness for acute and the bluntness of the obtuse, the closedness of the acute, and the openness of the obtuse that makes them acute or obtuse. Okay, those are pretty much all the terms that you need to know to start out. Like any technical terms, you want to get them sunken into your subconscious mind so that when you hear your teacher say them, you'll know instantly what kind of angle we are talking about. Now, this has been about straight lines on a flat surface, because straight lines on a flat surface are easy to understand. However, the whole point of perspective is to make a flat surface look like it's a window into a three-dimensional world. Italian artists in Florence figured out how to do this trick during the Renaissance 600 years ago. Here is a German, Albrecht Dürer, who picked up the torch, showing us how they worked this out. This is a musical instrument. This is a foreshortened picture of the musical instrument. This over here is a fixed point that represents a human eye. And this string is like a laser beam of light that goes from one point of the instrument to the eye and through this frame. Look what this gentleman is doing. He's placing the end of the string at a particular point on the instrument, and this gentleman is placing two crosshairs, one vertical and one horizontal, and they will meet at the exact place that that string goes through the frame, which is the picture plane. Now, do all that work? Close the little window, put a little dot, do it over and over, make a whole bunch of dots, connect the dots, and look what you've got. You've got a picture of a musical instrument. That's how perspective works. It's not guesswork. It's a science. We're going to study the science from a little different angle. Let's look down on someone as we often do in life. When we place in front of him a window which will be the top edge of a picture, and we place on the other side of that window a pencil of a certain length and another pencil of the same length but a little further away, and then we run lines from those ends toward that eye right in the middle of his head, like a camera. One eye is plenty. Look where they intersect on the picture plane. Now let's do the same thing with the closer pencil. Look at that. It intersects the picture plane farther to the left and right. You say, so what? Watch, watch, watch. If we flip that picture plane down so that we see what he sees, this pencil will be this long, and the closer pencil will be this long. Isn't that amazing? That's the way perspective works. The picture plane solves all the mystery for how deep space translates onto a flat surface. Okay, now let's get to the 5 ways to make a flat surface look like it has depth to it. It's an amazing magical trick, and there are 5 ways to create it. The first is diminution. Same root word as diminish. It means that as things move away from you, they diminish in size. So if we have a red circle, and then we do another red circle, and another red circle, and another red circle, and another red circle, and another red circle, they appear to be going away. They're not. If you put your finger on the screen there, you'll find that they're all the same distance from you, but they look like they're going away because they diminish. So if you want to make something look like it's going away, make it get smaller. That's diminution. A classic way to create the illusion of depth. Here's the next one. Foreshortening. Objects often have a long side to them that we call their long axis. When you bring one end forward, it gets shorter. And the more you bring it forward, the shorter it gets. That's foreshortening. It happens on cylinders, and it happens on 2x4s. When they tip forward, they get shorter, and when you put rubber bands around them like that, those are called cross contours. We'll get to those. There it is, an example of foreshortening, a second way to create the illusion of depth. Here's a third way. Foreshortening can happen in a very specific way when there are parallel lines. They come together. That's what converge means. They converge somewhere out there at a point. Now, it may be way outside of the picture, or it may be right here in the picture. Convergence happens when parallel lines go away from us. They will meet somewhere out there at a vanishing point. Look at this horizontal line. Let's make a line that is oblique to it. Okay, here's a question. Is it acute or is it obtuse? Depends on whether you're looking at the left side or the right side, doesn't it? Could be obtuse, could be acute. Okay, let's do another one. Now, there's not a single parallel line on the screen, and there's not a single right angle on the screen. But as soon as I put in another horizontal line, now we've got a couple parallels, but no right angles. So now what we have here looks like a balancing scale on a triangle, but with just a little magic, it could be a deep space picture where we would have to walk many steps to get over there to that tree. Or it could just be two horizontal lines in a triangle. Hey, watch what we could do. We could make them look more three-dimensional by a little trick. Watch this, watch this. Or we can do another one. See how the lines stay the same thickness as they go away? Let's make them get, ready? The principle of diminution. Wow, magic. All right, let's add a fourth way to create the illusion of depth. Air is not entirely invisible. So if we add a little fog, we are adding what is known as aerial perspective or atmospheric perspective. The atmosphere may be pretty invisible, but if you get enough of it, it starts to fade things out. So let's look at those circles that were going away from us, and watch this, watch this. Now it looks like they're really going away. All right, we've got 4 ways to create the illusion of depth. Here is a 5th way, and it is the one you understood when you were a kid. It's overlapping. We have the big ball close to us, and we have the small ball far away from us, but when we overlap them, it's really clear which one is closer. But hey, who is to say that this one isn't closer? Overlapping trumps the others because when one set of lines interrupts another set of lines, we know that the interrupter is closer. So there we are. Those are the 5 ways to create the illusion of depth. There are 3 dimensions in the 3-dimensional world. We can call left and right X, up and down Y, and front and back Z. Call them any names you want, it's just a way of saying that there are 3 dimensions in space. If we look at this from a view where we see the honest-to-goodness right angle of the height and width, the depth points right at us and all we see is a green circle. We'll call that a front view. If we get above it and look right smack down on that yellow peg, we see this. And if we want a side view looking right at that magenta axle, we see this. You see, a piece of paper doesn't quite have a third dimension, so we use these line systems to track the illusion of a third dimension. There's the whole theory. If you can look over this chart until you understand it, you pretty much understand what architects have known for centuries. We need 3 kinds of lines to show 3 dimensions, and we need more than one straight-on view to figure out how to draw an object in an oblique view, which people call a 3/4 view, even if it's not 3/4. Okay, now let's look at this need for more than one view and the difference between shapes and forms. Shapes are flat. Forms are thick. A square is a shape. If we pop it out of the flat surface into the world of form, it could be a box. In this instance, a cube. A rectangle could be a box, but we don't know for sure. It would be a box if from the top it looked like this, but not if it looked like this. It would be a cylinder, a can. It takes another angle to know. What can a triangle be? A pyramid if the top view looks like this, but if the top view is a circle, it's got to be a cone. We can't know the form until we see the hidden view, and a circle could be a sphere, which is a circle whichever way you slice it. Shapes are 2 dimensions. To know their forms, we need to see the hidden dimensions. That's why blueprints show multiple views, and why we need multiple views to draw in perspective. Well, I think we've come to the time where we should talk about how to get good at perspective. It's the classic way, it's the simplest way. It's by learning how to draw the simplest thing that looks 3D, the box. More specifically, the cube. Because cubes are squares on all 3 views, 1 by 1 by 1 measuring units, you can't make a simpler box than a cube. That's why you draw them over and over until you know how every angle looks in every position. I recommend that you do them freehand, and if you can, enjoy them. It may take a few dozen hours to master those angles, but when you have mastered cubes, you have mastered the 3 line systems of the physical universe. Now, if you get to where you can draw accurate cubes from imagination, you may get bored with cubes. That's when you try drawing everyday objects and see how boxily you can reduce them, like these. Don't get complex until you can package the form simply within a set of right-angled walls, and then within that scaffolding build the complex form. But the secret of controlling complexity is to relate every line back to that cube. It helps to chart out those 3 views so that you can compare that absolute top, side, and front, those are called draft views, with your oblique view. Now, you may struggle with it, and you may get it wrong until you learn more, but it's a struggle that strengthens your ability to imagine that secret 3rd dimension and track it. Here is what we all must do to master a complex skill. It all comes down to simplifying. This is a drawing I did back in the early 1990s in preparation for this illustration. Pre-computer, done with airbrush and ballpoint pen. It's basically a box within a box and some exploratory drawing to find the other parts. All that happens previous to the nice clean lines in the airbrush rendering and the ballpoint pen. Here's the point. We understand complex objects by breaking them down into simple forms within forms within forms. So once you have the tools of cubes and cylinders and spheres, you have the tools to build anything you want. In 1994, I gave perspective lectures at Fullerton College that a friend videotaped from the back of the room. This was 20 years previous to my current aged face, but it was about as clear as I ever explained it, and if you find perspective difficult, this will help you learn it with much less pain than books. We're going to spend a total of 12 sessions counting this intro. Here's the outline. We have begun with this intro to perspective that we're doing now. We will then spend 3 lectures on right angles. We will spend 3 lectures on circles, and then we will culminate the knowledge combining the two, circles and right angles combined. When you can combine blocks and spheres, you can create just about anything. Well, we've got a couple other things. We have surfaces that are not level, stairways, streets in San Francisco, box flaps. Those are inclined planes, and the vanishing trace will help us find where the vanishing points for non-level lines are. And then measuring systems. I'll give you 5 ways over 2 lectures to measure windows back in space, picket fences, checkerboards, or anything else equal or not equal. Depth measuring systems. And finally, plan projection, which is how you use blueprints to make a 3/4 view drawing. That's a semester's worth of subjects, and that's what we're going to deal with from these lectures I did in 1994 that we happened to videotape from the back of the room. I hope they help you get a grasp on perspective. If you want to know when I offer live critique, get on my mailing list, and I will let you know when I teach live, when I present new videos, and how you can submit work for feedback. In the meantime, I hope that these 12 lectures will help you to master classic drawing.